Okay, hi everyone for the third time today. Well, this is my last talk, and the focus is to give you an example of the practical use of this SIF information, which is within the context of the hyperspectral remote sensing. Specifically, the study I'm going to present, or the results that we have achieved so far, and I am going to present, is about the spatial relation between the SIF retrieved from airborne platforms and the water available for plants in the root zone. Since this is, well, we have done this in a framework of a study or an article, which again is not finished so far, but we have in this article format. Then I will present, I will give you the presentation in a similar format, giving the introduction first, with the context and initial concepts, then the methodology, and then the results. And within the results, I will give you some comments of why we think we are finding some conclusions. Well, no, some information or some new data into our maps. Okay, so let me start with the introduction. As a global concept, as a global context, sorry. Well, have in mind that agriculture is one of the most water demanding activities. And it is also not efficient using this resource. So remote sensing approaches have been developed, or remote sensing studies have been done, trying to help the agricultural sector to better understand the water status of the crops, aiming to create or to have better water management practices. The SIF is within these remote sensing tools that have been used for this issue. And yeah, the goal, what we want to contribute with this study is to provide information to improve the water use efficiency of crops at the end. So the big question we had at the beginning, if we want to use SIF data to monitor water status, then the first big question we had was, well, how this relation behaves. Does the SIF, this small red signal, increases or decreases when we have more or less water in the soil, or it doesn't matter, it does not vary according to the water in the soil? Well, we first wanted to clarify this. I presented these slides before, but I will go quickly through them. Well, again, the SIF is this red light emitted in two frequencies, which is, by the way, low intensity one. Then have in mind that this is a direct indicator of photosynthesis. And as I presented before, the SIF is the portion of the absorbed light that is re-emitted in red frequencies. And near red and far red frequencies are the terms used for the two SIF lights emitted. Okay. Now, why using SIF for water status assessment? Well, because being related to photosynthesis, then it can give us information or reflect physiological reactions happening in the plant before other processes happen, like leaf warming or pigment alterations. It is not always the case, but it can happen. And we think it could happen when we have not established stress conditions, but mild water stress conditions. This is what we think at the beginning of this study. And it has been used, the SIF, for water stress assessment but not so widely. I mean, there are few, well, not few, but some articles or studies that can be mentioned. For example, there is one from Alex Dam from Zurich University. It is, I would say, close to be published, who worked with the response of SIF in the temporal domain to different water stress conditions. And yeah, he found that the SIF actually detected earlier this water stress compared with, for example, vegetation indices. But again, this is not a war between SIF and vegetation indices. This is just to show when the SIF can work differently from the vegetation indices, and therefore how these two sources of information can be integrated. From the previous efforts, well, the first effort in this direction of comparing soil properties and SIF data was done by Von Havel. He's also from Jülich, but from other institute. He did it in 2018, reporting a spatial relation between soil properties, specifically soil electrical conductivity, and the sun-induced chlorophyll fluorescence. He reported this relation in one agricultural field. Then the last year we presented an abstract in the AGU conference when with other collaborators we found a significant spatial match between SIF and the spatial distribution of soil units in cases where vegetation indices remained homogeneous. Then, well, these two first efforts were done with high resolution data, but there are others that have been done with coarse resolution information. When I say coarse, I am talking about kilometer scale. I mean, pixels of kilometers size. But similarly, at this large scale, they found some more sensitivity or some higher sensitivity of SIF compared with vegetation indices to changes in the surface soil moisture. We think that our advantage in this new study that I'm presenting here is the high resolution of the data we have from both, from the fluorescence side and from the water available for plants in the soil side. And we think that having this kind of high resolution, we can be able to detect slight differences in the water status, not big differences when, for example, when there is an established stress and the plants are already getting, already drying. But we think that this high resolution information can help us to understand differences in the water status before it is too late. I mean, when the plants are still more or less greens, all of them, and there are some things happening in the plant that you cannot see with your eyes, but then the SIF could tell you something about it if you have this high resolution. And at the end, we want to prove this or to study this because we think that providing this knowledge, then we can, or this could help to better direct site-specific water management practices of crops. Site-specific, let's say, the precision agriculture or precision irrigation, or, well, there are those are close concepts. Now let me pass to the methodology. Well, the study was done in West Germany, in Jülich. We worked with information from several fields and 3 years. The fields are varying in area, and at the end we had information from 5 crops, which are sugar beet, winter wheat, barley, potato, and pea. And, well, I think, well, I don't know if it is also hidden in your screen, but in mine it is, but I will mention the text in the bottom in green letters that I put. It clarifies that this study was done with mild water stress, not with established stress, because we think that if we want to work with site-specific water management practice, then we should work before it is too late in the crop. So yeah, the study is done in mild water stress conditions, not established ones. And well, this is the methodology. It has several steps. I will try to summarize it to make it more simple for you. Well, at the end, if you look in the order of the panels, they have A, B, C, D, E labels, so we will go in that direction. In the first step, the A step, well, we have information from the high plant. We had SIF information from the high plant, and yeah, I mentioned already what is SIF, what is the sensor before. With this information, we computed the FCVI that I also mentioned in my last talk. We computed in order to downscale the SIF data, the original SIF data. So at the end, we had a downscaled SIF maps for 3 years, 2018, 2019, and 2020. Yeah, this was done from the side of the remote sensing data, the airborne remote sensing data. Then we also used Sentinel-2 information, specifically to compute evapotranspiration data for the 3 years. We computed this evapotranspiration using the CNET plugin from the ESA Snap platform. With the evapotranspiration data computed, we created evapotranspiration curves of the 2.5 months before the airborne data was collected. I will tell you in a while why we computed this evapotranspiration. Sorry. From the soil part, we have originally detailed descriptive soil map, which was produced with based on geophysics principles and electrical conductivity and so on. And all the science, all the soil science behind this map is published in Brohi et al. You can, if you are interested, you can look at it. But it is descriptive at the end. It gives us labels of 18 different soil units. And on the other hand, we have numerical data of fluorescence. Therefore, we needed to convert this descriptive map to a numerical map where each soil unit has one value of water available for plants in the root zone. And we did it using water retention curves. I will not come into detail what are the water retention curves and how they were used to convert the descriptive map to the numerical one. But yeah, just keep in mind this term, water retention curves, and then we got the numerical information about water available for plants in each soil unit. The problem at this point was that, okay, we had this numerical information from the soil, but we had only one single map. Then we needed 3 maps, one map for each year that could be compared with each individual yearly map of fluorescence. And for that, we computed a correction factor, basically taking the precipitation data as the main input in the system and evapotranspiration data as the main output. We took the accumulated or the area under the curves, the integrals of both variables for the 2.5 months before the airborne data acquisition. That's why a few minutes ago I mentioned the computation of evapotranspiration with the CNET plugin of ESA. Okay, with this, sorry. With these correction factors, we were able to transform the one single map of plant available water, of water available for plants in the soil, to 3 maps for each year. And then we extracted the individual maps for each field analyzed, and we overlapped it with the fluorescence information and estimated the relation between both. This is in principle the materials and methods. Sorry. For example, for the conversion of the descriptive data to the numerical one, I know it should be used, I mean, ideally, it should be used full model of soil plant atmosphere continuum, but we had not enough data. Sorry, so that's why we had to use to compute these correction factors. Just to give you a little bit more detail about the correction factors, again, the area under the curve of the evapotranspiration, the 2.5 months before the airborne data acquisition, was taken as the main output of the system, and the one from the precipitation as the main input. These are the curves that we computed. There is one curve of precipitation for each year, and there is one curve of evapotranspiration for each crop or each field analyzed, each individual field analyzed. And these are the correction factors, just for your reference. And now let me pass to the results. And let me take a little bit of water. Okay, here I'm going to show you first the maps of both variables. On the, I mean, the maps on the upper line are the fluorescence efficiency maps, and the maps below, which are polygons colored with green, yellow, and blue tones, are the plant available water ones. This is just to show you visually how they look like. And you can see in some specific fields that there is even a visual match between both variables, but this is not always the case. And moreover, just to highlight one other result, you can see low fluorescence in the winter wheat fields. And this is due because of the advanced growth stage where they were. The vegetation was not yellow yet, it still was mostly green in these winter wheat fields, but already it was fluorescing less. Maybe because of chlorophyll decomposition for nutrient translocation and yeah, other agronomic processes there. These are the maps from 2019 and 2020. Again, you can see visual match it can be seen in some cases, but not always. And that's why we decided to proceed with a numerical analysis to truly compare both variables. These are the results of this numerical comparison, numerical analysis for 2018. Here you can see the plots on the left-hand side. In the y-axis, you have the down-scaled fluorescence information. And on the x-axis, you will see the water available for plants in the soil information. The units of this water available for plants are liters per square meter. And you can see, well, we found a strong positive correlation between both variables in the non-irrigated summer crops, which are for 2018 sugar beet and pea. And we think that this is related to the time in the day where we collected the data, which was around 10:30, which is in the diurnal course of SIF. Generally, a moment when SIF is increasing along par photosynthetically active radiation and photochemical activity or photosynthesis. Therefore, we think that this may indicate as a greater photosynthetic rate or greater photosynthetic rates in the higher powest zone. I mean, in the zones where the soil had more water available for plants. And we did not find a relation in winter wheat, neither the irrigated potato field. For 2019, similarly, we found this strong, or well, the better relation or the significant relation between fluorescence and water in the soil into crops, in the non-irrigated summer crops again, sugar beet and barley in this year. And we found no relation in the irrigated potato field. A potato field also, of course, a summer crop, but in this case was irrigated and not non-presenting relation. And finally, in 2020, we found no relation in any case. So this lack of relation in 2020, which was a year where we observed precipitations the 2 to 3 days before the higher plant campaign, and in combination with the no relation observed in the irrigated crops, made us to think that the spatial relation that we saw, for example, in sugar beet and pea and barley irrigated fields, is broken whenever the water is not a limitation anymore. For example, when you have enough rains before you collect the data, or when you have an irrigated crop. So the SIF is, once the water is not a limitation, then the SIF is driven by any other factors. Could be even chemical soil properties, for example. And then we did also analyze on a specific plot where we observed the SIF reacting to a lower, to a zone in the soil that had a lower water content. In that case, the SIF was reacting before we saw responses in vegetation indices. In this case, we used the EVI, which is called, I think, the Enhanced Vegetation Index. But just let's think about it as a vegetation index. And we observed, if you just look at the panel C, that this anticipated reaction or effect in the SIF data happened in the spatial domain about 50 meters before the vegetation index started decreasing. And just to show you, in the panel F of the figure, you can see in the RGB image that this was not obvious on field. So we think that this can potentially be an evidence of anticipated detection of soil areas with lower water content detected with the SIF data compared with the vegetation indices one. And as I said, okay, this is an ongoing research. We haven't finished yet. And we are at the point that we are trying to, well, understand why in this specific field, the SIF was behaving in that way, different from the vegetation indices, because this is not always the case. And well, yeah, we are just discussing the hypothesis that even if it was, the image was captured in a very specific spatio-temporal point, at the end, we think that we capture an ongoing process. So maybe what we saw there, this anticipated detection, could be not seen in another time in the day or in another growth stage of the crop. But this is like the hot topic now, being discussed, and we are so excited, by the way. And yeah, now let me go briefly through the conclusions. Well, we found this strong positive relation between chlorophyll fluorescence downscaled to the leaf level and the water available for plants in the root zone of the soil, We observed it in summer crops. And we think that it is related to the time in the diurnal course when we collected the SIF data, which was around 10:30 a.m., which is a time that we can expect or think that the SIF was increasing alongside the PAR and the photochemical activity or photosynthesis. Then, well, we found a relation in winter wheat, even if it was not yellowing yet, but it was fluorescing less, and with no relation at all with the water available for plants in the soil. We think that this is because of the advanced phenology. Then we found no spatial relation between SIF and the water in the soil. When the water is not a limitation, we saw it in two cases, either if it is an irrigated crop or if we had enough or significant precipitations the days before the airborne data acquisition. And finally, we are analyzing some data that can show evidence of anticipated detection of lower zones of zones in the soil with lower water content with the SIF data compared with VIs. And again, this is an ongoing investigation we are doing. And yeah, I hope even so it was interesting for you to know. And just connecting with the original objective and the original question we had, well, we think that with this study, we can contribute with knowledge about how the SIF, the chlorophyll fluorescence, can be used to better direct water management practices in the real world of agriculture, according to the specific requirements of crops. And very important, all of this in a context without established water stress. Because if we move to that context, then if there is an established water stress, you will have smaller plants or plants getting totally different colorations, and then the differences you will see in that case in the SIF will be even super close to the vegetation indices. So that's why all of this that we are trying to provide with this study works in non-established stress or mild water stress conditions. And yeah, of course, you will have the references there. I hope mine will be in a list like this soon. So yeah, I hope you enjoyed the topic. That's from my side.